So the first question asks to remove all trailing zeros. The constraints are pretty small. Probably ON square works too, but it is very easy to do in ON. Not sure why they set up such a low constraint. Anyway, the solution is very straightforward. Just convert the input string into an array and then keep popping the last one until the last one is not zero. And then finally just convert back the array to a string and return it. For the second question, to begin with, there is a top left RC and a bottom right RC. The top left RC means the number of distinct elements you can see starting from RC. Keep doing R minus equal 1 and C minus equal 1 until you are out of the boundary. Similarly, bottom right RC means the number of distinct elements you can see starting from RC. Keep doing R plus equal 1 and C plus equal 1 until you are out of the boundary. After getting those values, answer RC just means the difference between top left RC and bottom right RC. Unlike its slightly overcomplicated problem description, the solution to the second question is actually straightforward because of the small constraints. For each location RC, we can keep doing R minus equal 1 and C minus equal 1 to get the top left RC, and R plus equal 1 and C plus equal 1 to get the bottom right RC. Then put everything you see while going through the path into a set. Because of the set is a distinct, so only distinct element will be counted, so we can just ask for the length of the set. So the total complexity is OH times W times max HW, for H is the height of the grid and W is the width of the grid. The third question probably is the hardest in this contest in my opinion. I barely solved it by the end of the contest. But it also turns out I overcomplicated a lot for the problem. Anyway, so the question is like this. Given a bit string with only 1 and 0, for each time you can choose a prefix of any size in nest or a suffix of any size in nest and flip it. By flip it, I mean changing 1 to 0 and 0 to 1. And after doing that, it counts as one operation. And the subcost of this operation is the length of that prefix or suffix that we chose to flip. Now, we want to know the minimum number of total costs needed to make everything in S become all zeros or becomes all ones. I couldn't understand the intuition behind a simple solution, so I will just explain my solution here. I solved it using DP. Think of the answer in this way. Fi flipped it 1, 0, where I is a number, meaning we want to consider S from index I to the end. Flipped it is a Boolean, meaning if the current state is flipped or not. And finally, 1, 0 is also a Boolean, meaning we want the whole string to be 0 or not. Our answer is one of the two, F0 false false and F0 false true. They mean getting all ones and all 0 respectively. For each Fi flipped 1, 0, we can get the actual value by first getting Si, then flipped Si if flipped is true. After that, if the actual value is the same as the expected value, then we just increase the index by 1 because we don't have to do anything here. However, when the actual value is not the same as the expected value, it means that we have to do something in order to fix Si. We can either fix it by flipping the suffix starting from I, or we can fix it by flipping the prefix. There's only two options, right? So one tricky part here is that while flipping the prefix, we want to choose Si plus 1 if Si is equal to Si, simply because if Si does not match and Si plus 1 is equal to Si, it also means that Si plus 1 will not match 2. The similar argument can be applied for Si plus 2, Si plus 3 as well. So we just keep finding until we reach a point that Sk is not equal to Si. Then we flip from all the way to S0 to K minus 1. However, remember previously we should have everything already fixed before reaching this index I. So now if we flip S all the way up to 0 to K, then they will become unmatched now. That's why we have to flip I minus 1 prefixed to fix them. In this way, we can recurse every possibility, then we just need to take the minimum of those. We can add LU catch in Python to quickly add memoized DP to our solution. Finally, both time and space complexity are ON. The fourth question is called maximum strictly increasing cells in a matrix. It is also a very tricky question. However, the problem statement is actually very similar to one of the problem that I have solved. It's called longest increasing path in a matrix. So it makes the understanding part of the solution a bit easier for me. In fact, the problem statement is exactly the same as it is for the longest increasing path in the matrix, but specifically for this problem, we can move the whole row or the whole column each time instead of just up, left, right, down. So basically we start from any cell that we want and then keep finding the next larger value if it is on the same row or if it is on the same column. So the question asks what are the maximum steps that we can take. Now, so how can we solve this problem? I think it is a very interesting problem. Feel free to stop at any point while I'm going through the solution. If you already know how to do it, stop the video and solve it yourself. It will be a good practice to try it on your own instead of just listening to my solution. So first, by looking at the constraints, we know any ON squared plus solution won't work because the n size is as large as 10 to the power of 5. Then, how about sorting? Instead of thinking the input as a 2D grid, translate it into a 1D array and sort them by their values and see what we can get. Okay, so now if we look at the 1D array, if we try first them from largest to smallest, we can be sure that by the time we are visiting the current index, let's just assume that is index I, we have already visited all the other index j, that is the other index that can potentially be I next. So we just need to pick the values that are maximum from the right hand side, which has the same row as I or has the same column as I. And after that, we will need to consider the maximum value that I can provide to the neighbor on the left hand side. So we will just have to update that maximum as well. So here is the code implementation. It is just what I have explained but in code, so I'm not going to bore you with details. So in total, the time complexity is O(n) log n because of the sorting, and the space is O(n), where n is the size of the grid. In conclusion, it is a pretty tricky contest. It also has been forever since I was able to solve all 4 questions. It will help a lot if you leave a like and a comment about your contest experience too.